All right, this one I kind of was hesitant to talk about this one because I'm really not sure on this. Neutrinos, they're their own thing. They're in a whole nother playing field. Everyone's very confused by what's going on with neutrinos and their oscillations and stuff. And I think that the oscillation of neutrinos um, is representative of um, the breathing in and breathing out that I've talked about in other videos about, like, electrons are breathing in and breathing out. Basically, they consume energy in and then they send energy out. And I think that this oscillation pattern that we notice with uh, neutrinos from like our limited observations, I believe is something to do with those lines. I don't have the most knowledge on the subject. I don't know if the oscillation pattern is sporadic, but I would imagine that it wouldn't be called an oscillation if it was sporadic, because then it's not really oscillating. It's just random. It would probably be considered more of like a quantum superposition kind of thing rather than consider this oscillation pattern. So I'm not 100% certain, but from my understanding, you know, particle neutrinos are made, and then they will oscillate between sizes and stuff. And a potential reason why we think neutrinos are the only ones that do this is because their size is just big enough to notice, but small. It's like the perfect size where it's big enough that we can see a difference, but but also small enough that we can see a difference, right? Because um, when you think about the energy change, right, for larger mass objects, say like an electron, when we look at it, its size may be large enough that its mass variation is, 5 decimal points down the line from whatever its number is. Like on like an MeV like standard, it may be a difference of like 0.00002, right? When it's at its height, it's at its peak, it's, at that, like, we'll say, just to for ease of numbers, it's at 1.0002, and then when it's at its low, it's at just one even. Like a difference like that would be really hard for us to, chalk up to anything other than uncertainty. And maybe it's a smaller difference than that. Thinking about the size of a neutrino in comparison to an electron, like they're really tiny, right? But when you look at a neutrino, we have like their measurements, and we say, oh well, they are, this size. So when we're looking at them with this precision, we notice a larger, like, discrepancy in size, and so we say, okay, something's going on here. But maybe, I mean, I don't know, I'm not doing the experiments, but maybe like electrons are doing something similar, but we just don't notice it because we weren't looking for it, and two, it can easily be chalked up to just measurement error or other noise, like, things, right? So it could easily be brushed aside if we did find it in other places, but it could have been just ignored because, again, we weren't looking for it. And so, with photons are smaller than neutrinos, and so they're potentially too small for us to notice that difference in, like, this oscillation and stuff, because we see wavelengths. So it could, maybe that is, there's, like, as the light travels, it is oscillating, and we see this wavelength because of this oscillation, but we don't know. We haven't made that connection. I'm not sure. I'm just putting things out there. But pretty much what I'm saying is that I feel like this oscillation is a good pointer towards me being on the right track, so long as it is what I think it is and it works how I think it does. Um, but I do think that uh, they gain and lose mass over time because they have this breathe in, breathe out, and it says, okay, well, what are they breathing in? Well, they're breathing in these virtual particles. Basically, neutrinos are just they don't they neutrinos are like neutrons where they're kind of like a neutral particle, but um, instead of binding to uh, other things, I think neutrinos are like actually more of a neutral, balanced. I think a better term would be like, I feel like neutrinos are like a cross between a proton and a neutron, right? They have the neutrality of a neutron, but the self-sustainability of a proton, because a proton doesn't need anything else to be a proton, right? But you don't find solo neutrons. They're hanging out with other protons, and you don't find solo electrons for long. They're always trying to find you know a proton to join up with. And so I think that neutrinos seem like this almost ghost particle because they're in this neutral state where they're able to farm enough energy. Because their size is so small, they can farm enough energy from virtual particles they interact with that they don't actually need any outside they don't need energy from anything else. They can survive off of just consuming the virtual particles they collide with as they zip by, right? And so they seem extremely unreactive because they don't need anything. They don't need to react with anything else to get what they need to continue. And I think that when they're in a state of consumption, they grow in mass, and then as they, kind of release that energy over time, then they reduce in mass again. And so we see this happening, and this is, I think, more evidence towards, because it's like, where is this mass coming from, right? It's coming from the virtual particles that they interact with. And I just think that it's a good pointer towards, one, this breathing in, breathing out, two, consumption of virtual particles for energy, and three, on another note, neutrons are not neutral. Because if they were, they would probably do something similar to neutrinos, except they would be colliding with stuff all the time, right? So that's why they don't do that. And so, yeah. I think that's pretty much all I wanted to say with that, And I also think tying it in, like the fact that we know that neutrinos have mass and are so tiny, I feel like it points towards the credibility that photons could have mass too, because they're, if we can't really tell, if the main reason why we think neutrinos have mass is because they oscillate, and we know they oscillate, but we can't really tell their mass, then I think it stands more to reason that light could also, like photons, could also have mass. So I think that that's another thing as well. It points towards everything with energy having mass on some level. And yeah. I think that, I guess I'll talk about this too. Having the different states of, or the different flavors of the particles, I think this is pointing towards this points towards also there being this breathing in, breathing out of energy by all particles, because they all have three flavors. And these three flavors, I think, they don't, the only ones that last long and are stable are the lowest energy level ones, there, which are standard ones we know about. And the other ones, they decay very quickly. And I think that the reasoning for this is that all of the particles are capable of holding higher amounts of energy. And so we only observe these larger particles when we collide them and we give them high amounts of energy. So they're capable of taking this in, right? But their balanced state is at at their level where their intake and their in and out is balanced. And so that's where they try to, and that's where they stay as their base point. And so the heavier version that we notice, that is the maximum amount of energy that they can sustain without they can like withhold before it's too much. And they just have to just, I guess, dump any more energy that comes in, or anything that they get immediately, like they're sending out. I'm really not certain about the process, but I would imagine that there's a limit to how much energy they can actually sustain. And so we see that as a separate particle, but they all act the same, because they all are the same particle. They're just in different states. And so the high energy state is the largest one, and then the state that's like in the middle there, that's like in between them, that is like the transition state. It's not necessarily that like they're all, it's like boom, 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 these three different things. I think that it's this like different, they're just transition states. Because if they were their own individual particles, why would they only exist when we make them, basically? If they were their own individual particles, they wouldn't only be found in our colliders. So and the fact that they act the same way as the other particles just points more towards the fact that they are in fact those other particles. And they decay so quickly because those states are not stable. They're not a stable state. They're not at equilibrium anymore. So the particle has to become, it has to release energy to get back to its equilibrium point. And so that's what I think is going on there. That's why we got flavors. That's why neutrinos oscillate. That's why everything, I think, oscillates, honestly. But yeah. So, peace out.